Okay, hello guys. Let's check it's working. Today I made the live public. Yes, I think it does work. Okay, so for today we planned to finish paper 1. Remember last time we solved the first 16 questions from IB HL practice paper 1. The link would be for the paper would be down below. It's from Save My Exams. So last time we solved 16 questions and we have 40 minus 16 left. So let's start from question 17. The first part is in another video. You can find it on my channel. So question 17. Which volume of oxygen, let me see actually, how can, do I block my screen a little bit? Yes, okay. So which volume of oxygen measured at room temperature and pressure is needed to complete combustion of 0.1 moles of propane? Okay, so combustion is reaction with oxygen. Propane is C3H8. So we do C3H8 and O2. Since it's complete combustion, we know that the products would be CO2 and H2O. So for organic compounds that contain CH or CH and oxygen, the products of complete combustion would always be CO2 and H2O. It has to be balanced because we need the molar ratio, right? But what do they ask? Yeah, they ask the volume of oxygen, which means that we have to fully balance it. But normally, if they ask, for example, for the volume of CO2, then you don't have to balance the whole thing. You just need the ratio of C2, like C3H8 to CO2. But here I do have to balance properly. So, okay, the combustion reactions we balance in order of CHO. That's the fastest way. So on the left side, I have 3 carbons, on the right 1, so I put a 3. Then hydrogens. It's 8 on the left, 2 on the right. So to make it 8, I put a 4. Now it's 8, 4 times 2. And let's carefully calculate oxygens. So on the right, it's from here I have 3 times 2, and from water it's 4 oxygens. So what is it? 6 plus 4, 10. Yeah, so I have 10 oxygens on the right, and to make it 10 on the left, I have to put A5. Now it's 10. Then which volume of oxygen is measured under room temperature and pressure is needed for complete combustion? So we know that the moles of propane is 0.1. And since the equation is balanced, I can find the moles of oxygen that reacted. So the ratio is 1 to 5. We're looking at the coefficients, right? So 1 in front of C3H8, 5 in front of O2. So moles of oxygen would be 0.1 times 5. And then oxygen is gas. For gases, I can apply the formula that volume of gas equals to moles times molar volume. The molar volume, be careful with molar volume. If they don't give you the molar volume, but they give you they say that the reaction was done in standard conditions, or at least the volume was measured under standard conditions, then that molar volume is in the data booklet, it's 22.7. Here they gave you molar volume for room temperature and pressure. So they could give you a molar volume for some other conditions. So it's not always 22.7. 22.7 is only for STP. Right, so I do 0.5 times whatever molar volume they gave me. They gave me 24, so it's 12 dm cubed. So A. Next question. Which alcohol is not likely to have a fragment at Me at 43 in its mass spectrum? So what does that mean? Its mass to charge ratio. It could be Me or Mz. So when you inject an organic molecule into the mass spectrometer, then you would get molecular ions, right? So it's the molecules that are not fragmented but just positively charged because electrons were knocked off. And you can find the M to Z value. Yeah, so M, it's the molar mass of the molecule, and E, it's the charge on the molecule. Usually it's +1. Yeah, so by default we assume it is +1. There could be tricky questions when 2 electrons are knocked off and it would be +2, but not in the fragmentation patterns at least. And some molecules, because their organic molecules are large, some molecules would be fragmented, and those fragments, if they're charged, we can also detect them. So basically, what does this question tell? So this question tells that the molecule is not likely to have a fragment with this molar mass. Yeah, so you can treat, especially in questions with fragmentation patterns, you can treat the m to e value as, or m to z value as molar mass of the fragments or molar mass of the molecules. But again, be careful, sometimes e is not 1, could be 2, but not in fragmentation questions for IB at least. All right. Well, and also when we're working with fragmentations, what you should remember is that it's best to break one bond at a time. There is a reason for that, because it's very unlikely that two bonds would be broken. Yes, so more likely that one bond would be broken at a time, and especially for the exam purposes, always break one bond. So for example, if let's see if A has the fragment of 43. So now what I will do is I will draw out the molecules, and I will check whether in the molecule, if I break one bond, I would end up with a fragment that has molar mass of 43. Well, let's try. So CH, that's for A. Yeah. CH3, CH2OH. And then, well, what's your best guess for a fragment that would have a molar mass of 43? Well, probably this. If I break this bond, yeah, because I have like three carbons, it's 36, and some hydrogen, so this could be close to 43. This, I don't know, I have to calculate. And now what I will do is I will just calculate the masses of each fragment. So let's calculate the mass of this fragment. So it's one carbon is 12 plus two hydrogens plus 16 is oxygen plus 1 is hydrogen. So molar mass of this fragment is 31. What about this one? Let's see. So this fragment, it has 3 carbons, so 12 times 3 plus 7 hydrogens plus 7. Yeah, that's exactly 43. So you see, if you have this molecule in your mass spectrum, so you will get a fragment, or you could get a fragment with the m to e ratio as 43, because this is the fragment with molar mass of 43. And I have to do this for all the molecules. Okay, so you have to redraw them if you need to, and then check whether you would have these fragments. But because I already know that, okay, basically C3H7, yeah, that has this molar mass. So I know that the second molecule in B, it also has this fragment. So you see this one, it's also C3H7. So I don't even have to redraw it. I can see that this molecule does have this fragment. So it's not A, not B. And also C, yeah, so this is the fragment. Again, C3H7, so this fragment has a molar mass of 43. So it must be D then, right? But let's check. So if I redraw D, I would get CH3, CH2, CH, OH, CH3. So probably the closest molar masses would be if I break this bond. Well, let's check these two fragments. Well, definitely not that one, right? Because this is C2H5, too small. But this one, let's check the molar mass for that fragment. So it's 2 carbons, so 12 times 2, plus 4, 5 hydrogens, so plus 5, and plus 16, that's oxygen, so 45. Right, so the most likely fragments would be this one and the one at 45. And then if you try, of course you can try, for example, and remove OH bond, but I can see that if I remove OH bond, then this fragment would not work because it has too many C's. Yeah, I know it has to be approximately 3 C's. So that's the approach. With these questions, it might take you ages to solve, so you have to be either well practiced or skip and return at the end of the exam. Okay, I'm not, by the way, checking chat, but okay, I hope that's fine. Next question. The mass spectra of 3 compounds A, B, and C are shown below. Okay, mass spectra. Again, we see some fragmentation patterns. Yeah, so we see this peak, that peak, this is also probably a peak, and so on. What evidence from the spectra of the 3 compounds A, B, and C suggests they could be isomers? Okay, isomers. We don't even have to look at no, we do have to look at the graph. Yeah, so isomers are compounds or molecules with the same molecular formula but different structural formula, right? So we know that these, if they're isomers, they must have the same molar mass because they have the same molecular formula. And molecular ion peak, it's the unfragmented molecule, yeah, that we just discussed, that okay, it would undergo fragmentation, but there would be a peak that corresponds to an unfragmented molecule, and that peak would be the one with the highest molar mass. Yeah, so molecular ion peak shows the molar mass of the molecule, and it would be the peak with the highest MR. So for example, let's look here. These are three spectra. Okay, so the peak with the highest molar mass, it's this one. It is tiny. Yeah, it is tiny, which just means that I hope they would give you a better peak. Sometimes it's a bit higher, right? So hopefully in the exam you would have a better peak. But it is a peak, and I know that this is molecular ion peak because this is the most right-hand side peak. So I know that the molar mass of a molecule is, what is that? That's this peak. So it's 70, 70, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, so one division is 1, so 74. So molar mass of A is 74. Molar mass of B, well, also 74 apparently. 1, 2, 3, 4. Yeah, this one, a molecular ion peak, and this one is also 74. Yeah, so molecular ion peak is at 74. So it's not the most abundant one. Yeah, the most abundant is the most stable fragment. That's why it's the most abundant. But it's the most right-hand side peak that shows you the molar mass. So it's they all show a molecular ion peak at 74. Next question. Again, I'm covering the text. Okay. A student mixed 30 cubic centimeters of 0.2 molar 0.025 molars potassium hydroxide, okay, that's KOH, with 30 cubic centimeters of 0.0525 nitric acid. The temperature rose by 0.5. Assume no heat was lost to the surroundings. What is the molar enthalpy change for the reaction? And we have specific heat capacity. Okay, so well, they didn't ask for enthalpy of neutralization. They just asked for the enthalpy change, molar enthalpy change for the reaction. But just in case, still, I recommend to write down the equation just to understand what's happening. If you don't know how to write the equation, that's actually not fine either. No, you have to, yes, you have to write the equation because you have to understand if you have a limiting reactant, yeah, then you have to calculate enthalpy change for the moles of limiting reactant. That's why it's still, you still have to write down the equation to know that it's 1-to-1 ratio and that there is no limiting reactant here. But so in these questions, I assume that if they don't give you the chemical equation, we would still write it. So I write it out. KOH and HNO3 gives you K. And this is, by the way, now is in the new syllabus. Previously, it was considered a prior knowledge. Now we study it in, what was it, in reactivity 3 in acids and bases. Yes, all the reactions of acids. This is balanced 1-to-1 ratio, all good. And I see that I have equal volumes and concentration for both, so there is no limiting reactant. I don't have to check. Yeah, so they both react in perfect 1-to-1 ratio. And okay, now we have to find what? We have to find molar enthalpy. So the first step to finding molar enthalpy is to find heat, which is Q equals to Cm delta T, and this formula is in your data booklet. So C, it's the specific heat capacity of the solution, which they approximated as 4.18, that's like for water. Then mass, it's the mass of the solution. Again, we can just assume that it's 60, so you're mixing 30 and 30, right? That's 60 cubic centimeters, and for water density is 1 gram per cubic centimeter, so we can just say that it's 60 grams. Of course, it's not water solution, but that's our approximation. By the way, in paper 2, they can also ask what approximations you did. Well, that's the one. N times 0.5. Okay, 4.18 times 60 times 0.5, that is 125.4. And what about the units? Look at your constant, you see, joules, so the units for the heat is joules. Then we find the moles of the limiting reactant. Yes, so here we don't have the limiting reactant, the moles are the same, so I can find the moles of either KOH or HNO3. That's concentration times volume, so 0.025 times volume in cubic decimeters divided by 1000. Yeah, that's 0.03. 0.03, which is 7.5 times 10 to the negative 4. And then we find enthalpy change. So enthalpy change, it's kilojoules per mole they want, right? Kilojoules per mole. I take my heat divided by moles, because we need kilojoules per mole, right? Then since I divided joules by moles, this would be in joules per mole. I need kilojoules, so to convert to kilojoules, I divide by 1,000. And then another very important thing, you have to plug the sign for delta H manually. So if the heat is released, that's an exothermic reaction, so enthalpy change is negative. How do I know heat is released? Well, because the temperature rose by 0.5. For endothermic, the temperature would have decreased, and then enthalpy change would have been positive. Well, okay, and I just calculate that. 125.4 over 0.00075 over 8,000. That looks like a D. D. Next question. The first stage, just double checking. Yes, I hope it's streaming. Let me just double check one more time. If it's still going. Yes, it does. Okay. It looks like it does. Let me just see. Yes. Right. Next, so the first stage in the industrial production of nitric acid from ammonia can be represented by the following equation. Using the following standard, I did close it. Yeah, okay, so using the following a standard enthalpy change of formation data, what is the value of the standard enthalpy change for this reaction? Right, so they gave us a reaction. Balanced equation, all good. And they gave us information about delta HF. Please do not draw the Hesse cycle even if your teacher forces you to, especially in multiple choice questions. You don't have to draw the cycle with the triangles thing. Because when I mark the questions and I see the triangle, I know that something will go wrong. Usually something does go wrong. So just use the formula. You can find enthalpy change of reaction from formation enthalpies as formation of products minus formation of reactants. This formula is in the data booklet now for HL students. Yeah. Right. So let's see. Formation of products. So what are our products? Our products are 4NO, 4 times 90.3 plus, that's NO, plus 6H2O gas, 6H2O gas, negative 241.8 minus reactants, delta HF for reactants, so minus, and then I open the brackets. For oxygen, enthalpy change of formation is 0 because it's an element in standard state, so it's not in the table. For NH3, so it's minus 4 times NH3. And then don't mess up the signs yet, just carefully with the calculator. You understand that minus times minus is plus, so just 4 times 90.3 plus, well, minus 6 times 241.8 and plus 4 times 46.1. It is minus 900, so that's negative 905.2. That's a B. Kilojoules per mole. Which process converts glucose to ethanol during the production of bioethanol? Factual knowledge, bioethanol is just normal ethanol but produced from, well, using yeasts, right, from glucose. So that is fermentation. Transesterification, it's when you have triacylglycerides and you substitute glycerol with methanol, for example. Photosynthesis, well, you all know what it is. Yeah, that's consuming, when plants consume CO2 and release oxygen and synthesize glucose in the process. Cracking, it's splitting long chain alkanes into shorter alkanes and alkenes or hydrogen. The equations below show for the formation of sulfur oxides from sulfur and oxygen. Okay, 2 equations. And by the way, these are enthalpy changes of formation. They wrote it as enthalpy change of formation of SO2 and SO3, but they could have just written as just delta HF, just delta H without the F. And it's good if you recognize that it is enthalpy change of formation. Why? Because you're forming 1 mole of a compound from elements in standard states. Right, and question is, what is the enthalpy change of reaction? of that reaction. So again, I have enthalpy changes of formation. I will not draw the cycle. I would use the exact same formula as previously, that enthalpy change of a reaction is formation of products minus formation of reactants. Delta HR, it's enthalpy change of the reaction. Yeah, so that's delta H of products minus reactants, and just plug in the number. So what are my products? My products is 2SO3, so 2 times negative 395, minus reactants. Reactants are oxygen is 0, again because it's an element, 2SO2. 2 times formation of SO2 is negative 297. 395 times 2 plus 2 times 297 is negative 196 kilojoules per mole, so D. Next question. Which of the following conditions will mean a reaction is never feasible? I think there is a typo in this question. You don't need obviously the temperature, because if it's never feasible, so it's at both temperatures, high and low. So I guess that's a mistake in the question. But again, this is from Save My Exams, right? So in the real exam, hopefully you will not get these questions because they would be moderated better. Okay, well, let's see. So which of the following conditions, so we just choose delta H and delta S, will mean a reaction is never feasible. What does never feasible mean? So feasibility of a reaction, it's like we can check it out from delta G, right? Gibbs free energy. Delta G, it's, well, okay, I'll try to be consistent, and all the formulas are in blue. It's delta H minus T delta S. Again, I think this formula is in the data booklet, but better to memorize because it's everywhere. Only for IB students, right? For A level, you need to know it by heart. Okay, and the reaction is never feasible. What does it mean? It means that at any temperature, at both low and high, delta G is positive. Yeah, so the reaction is not feasible when delta G is positive. Well, let's see. So if temperature is low, what does low temperature mean? Let's say 0, the lowest possible. Yeah, not achievable, but we can just say it's 0. So if temperature is 0, then delta G would equal to delta H, and delta G must be positive, so it means that delta H must be positive. So delta H must be positive, so it's not C, not A. And then if the temperature is high, well, what if the temperature is high? Let's say it's very high, let's say 10,000 kelvins, yeah? Then delta G is, well, this is a positive number, we already know that. And then minus a huge number, so huge T, delta S. So you see, if delta S is positive, it means that you would have a positive number minus a huge positive number. That would make delta G negative. But if delta S is negative, then minus T delta S is positive. So it's positive plus positive would also be positive. So delta S must be a negative number. So B. Right? And temperature, remember, temperature in this equation is in kelvins. It cannot be less than 0. Yeah, the lowest possible is 0 for kelvins. Next question. A 2.27 cubic decimeter sample of nitrogen gas measured under standard conditions reacted with a large excess volume of hydrogen gas to produce ammonia. Only 20% of nitrogen gas reacted to produce ammonia. What mass of ammonia was made? We need an equation, yeah? Again, we need an equation because the reaction is happening, we need to know the ratios. So we know nitrogen gas, it's N2, reacts with hydrogen, large excess of hydrogen, and produces ammonia. You need to know the formula, that's NH3, and then we balance. So to balance nitrogens I put a 2, to balance hydrogens I put a 3, and they say that 2.27 cubic decimeter, and then you see here at standard conditions, under standard conditions, if it's under standard conditions, I know that the molar volume is 22.7 as it's in the data booklet. So the first thing that I would do, and in these questions, remember what we do, so we always find moles first and then apply the ratio and then find whatever they ask, yeah, from the mass of ammonia in this case. So the first thing that I would do is I'd find moles of nitrogen gas. And since it's a gas, I'm applying the formula that it's volume over molar volume. So 2.27 over 22.7, that's from the data booklet, molar volume at standard conditions, which is what, 0.1, right? Yes. And then they ask me about, well, first of all, okay, so they say that only 20% of the nitrogen gas reacted, so that's like just an extra step, yeah? So I know that not the entire 0.1 mole reacted, but 0.20% of that, yeah? So nitrogen that reacted is 0.1 times 20%, so times 0.2, which is, if my mental math is right, it's 0.02 moles. And then I will apply the ratio to NH3, right? NH3, because they ask for the mass of ammonia. So moles of ammonia would be, it's in a 1 to 2 ratio with nitrogen. So 0.02 times 2, 0.04, and then I find the mass of NH3, because they ask for the mass of ammonia. So mass of NH3, it's N times Mr. This formula, I don't know if it's in the data booklet, but this one you just have to know. Ammonia NH3, so molar mass, nitrogen is 14.01, hydrogen 1.01. For paper 1, for like multiple choice, I can just round it to 14 and 1, so 17. Yeah, 14 plus 3 times 1, 17. But remember, for paper 2, you cannot round it. You have to use it, the molar masses as they are in the periodic table to 2 decimal places. Okay, 0.68 grams. C. Fine. Do I need to double check anything? No. Okay. Next question, 26. Which of the following factors will not affect the value of the activation energy of a reaction? Will not affect. The presence of a catalyst. It's the thing that lowers the activation energy, so it's definitely not 1. And if it's not 1, it means that it's 2 and 3. But let's double check. Yeah, if I have time, I always double check. Changes in temperature. Yes, activation energy does not is not affected by temperature, and obviously concentrations do not affect activation energy, so all good. 27. The distribution of molecular energies in a sample of a gas at a given temperature is shown by the Boltzmann distribution graph below. Okay, so Boltzmann distribution, right? We have, what does it show? So if you had a vessel with a gas and you were able to measure the energy of every single molecule, kinetic energy, then there are a lot of molecules, right? Billions of billions. And if you were able to measure the energy of every single molecule, you would get a distribution of energies that would look something like that. So it always starts at 0 and then it goes like up, but it's not symmetrical, and it has this tail and at higher energies which never intercept the x-axis. Yeah, so if you draw it, be careful how you do it. Yeah, so it should look like this. And question, if the temperature is increased, what will happen to the position of point X? So at a high temperature, what happens is that the energies, they shift towards higher energies, right? The energy of molecules shifts towards higher energy. So the peak becomes lower to the right, and the the ending of the curve goes above the ending of the curve at like the right hand side of the curve at lower temperatures. So this would be T2, this would be T1, and T2 is higher than T1. The area under the curve, remember, it shows the total number of molecules, so the area under the curve should roughly stay the same. But in any case, the okay, let's see. If the temperature is increased, so that's how the graph changes, what will happen to the position of X? Fewer molecules possess the most probable energy value. Yes, so that's the most probable energy. So X will shift to the right. Yes, X will shift to the right. That looks right. Let's check the rest. Fewer molecules possess most probable energy. Yes, so X will shift to the left. No, not to the left. More molecules possess the most probable energy, so X will shift to the left. No, not more molecules, right? We have less molecules because the peak goes down. And the position of X will stay the same. That's wrong. Okay. So x would, it's not so, it's and x would shift to the left, right? Because it's not really connected. More fewer, because fewer molecules possess most probable energy, just means that it would go down, and x shifts to higher energies. Yes, so not so, but and. Next one. Which systems are correctly described? Okay, well, let's see. So, open systems, it's when you have exchange of matter and energy. Closed systems, it's when you have exchange only of energy, and isolated systems, no exchange. Yeah. So open, everything is exchanged. Closed, only exchange energy. Isolated, don't exchange matter or energy. Okay, so matter and energy can be transferred across the boundary of an open system. That looks right. Only matter can be transferred across the boundary of a closed system. That is wrong. Only energy can be transferred. Matter and energy cannot. Well, then it's if it's not two, then must be 1 and 3. But again, let's double check. Matter and energy cannot be transferred across the boundary of an isolated system. Yeah, that's right. That is okay. Next one. In a reaction between 1 molar, this M, it's just mole per cubic decimeter. Okay. Concentration. 1 molar hydrochloric acid and in excess of marble chips, calcium carbonate, the volume of a gas produced was measured against time. This is shown on the dotted line in the graph below. The experiment was repeated, but this time using the same volume of 2 mole per cubic decimeter. 2 mole per cubic decimeter hydrochloric acid. Which line on the graph represents this experiment? All right, so the dotted line, let's see the graph. So the dotted line, this one, it shows 1 mole per cubic decimeter HCl, and that's it, right? And marble chips, well, that's a reaction of HCl and calcium carbonate. CO2 is released. And then the experiment was repeated, but but this time using the same 2 molar HCl. Okay. What's important here? So basically what we need to assess, we need to assess the rate of the reaction. So for example, C and D reactions, they go faster than our initial reaction because you see the gradient is steeper. Okay, and B and A are slower. So we know that it's not B, it's not A, because if you double the concentration, the new, like what the new conditions, the new conditions are 2 mole per cubic decimeter HCl. So we doubled the concentration and the rate increases. So we know it's not A and B because A and B is slower rate. But be very careful. If you increase the volume, the increase in volume of HCl would not increase the rate because you would have the same number of particles per unit volume. But concentration increase, it would always increase the rate. Because more particles per unit volume, more frequency of successful collisions. That's one thing. And then what else do we have to check? We have to check whether the amount of gas would increase or not. So for C, the amount of gas stays the same after you've changed the concentration. For D, it increased. And to figure that out, we have to understand which is the limiting reactant. And they say, what do they say? They say that we had excess of marble chips, which means that HCl is limiting. So if you increase the concentration of HCl, then you increase the moles of HCl, and then you increase the moles of CO2. Yeah, so you would get twice as much gas. So it is D. If marble chips were the limiting reactant, if HCl was in excess, then it would have been C. Yeah, so you increase the concentration, but the volume of gas doesn't change. I hope that's fine. Next question. Ethine. Ethine and hydrogen are formed from methane, and dynamic equilibrium is established. What are the units of Kc? Everyone's favorite question. Let's do it. So Kc, equilibrium constant, right? It is products over reactants to the power of their coefficients, and concentration at the square brackets denote the concentration at equilibrium. So H2 cubed, right, the cubed because there is a 3, divided by CH4 to the power of 2. And to find the units, so basically what do we have? Well, we have concentration to the power of 4 on the top, 1 plus 3, divided by the concentration to the power of 2 at the bottom. And you can work with this like you would with the numbers. So for example, if it was 2 to the power of 4 divided by 2 to the power of 2, it would become you do 4 minus 2. Yeah, so it's concentration to the power of 4 minus 2, so to the power of 2. And the concentration is in mole per cubic decimeter. So you have concentration squared. So you do mole to the power of 2. I open up, distribute the brackets. 2 times 1 is 2, and 2 times negative 3 is negative 6. So mole squared dm minus 6. Units don't show anything, just, I don't know, just a math exercise. Right, next question. The diagram shows a reaction pathway for an endothermic. Heat is absorbed, right? Which arrow represents the activation energy for the forward reaction? Well, activation energy is always from a reactant to the top. Yes, so these are your reactants, these are your products. So the arrow that goes from both exo and endothermic, that goes from reactants to the top, that's activation energy. That's a B. Yeah. What is this? This is like that. No, that's wrong. C, what would C be? C is the activation energy for a reverse reaction, yeah, when products go to the reactants, from product to the top. And D is enthalpy change. But enthalpy change, it should be denoted as one arrow, but like doesn't really matter in this case. Yes, we know it's not D. D is enthalpy change. So B. Next question. The typical reactions of dilute acids include them being able to react with hydrogen carbon. This is again that reactivity 3. We have 6 reactions of acids. Yeah, that's so one of them is with NaHCO3. Acids do react with hydrogen carbonates to produce salt, CO2 and water, so that's correct. And acids do react with metal, so they react with magnesium, but not with copper. Why? Because dilute acids would only react with metals that are higher in reactivity series than hydrogen. And by the way, they removed reactivity series in the new syllabus. So I will have to maybe show you someday how to use electrode potentials, but for HL it's fine. For HL you'll be able to figure it out from standard electrode potentials, but for SL, when we do SL, I'll show you how to figure out reactivity series from electrode potentials at some point. So magnesium is more reactive than hydrogen, so it would react with dilute acid. Copper is less reactive, so it would not. So only 1 and 2. Again, next question. Right, some species may be classified as amphiprotic, some as amphoteric, and some as both. Which of the following applies to HPO4 2 minus? Okay, so amphiprotic, what does it mean? Amphiprotic, it's the species that can gain and lose a proton. Yes, it's about protic, yeah? So the substance that can both gain and lose a proton. Amphoteric, it's a more general term. It's a term that just says that the substance can act as acid and a base. So amphiprotic shows you that the substance can act as acid and base because it can gain and lose a proton. But using Bronsted-Lowry definition of acids and bases, yes, so acids is proton donor, base proton acceptor. Amphoteric, it's a broader term because you also have Lewis definitions of acids and bases, yeah, when there is a lone pair being donated or accepted. So if substance is amphiprotic, I'd say it should be amphoteric. Probably that's the correct way to say it. Yeah, because if it can gain and lose a proton, then yes, it can act as both acid and base. So it will be amphoteric. Well, let's see. So HPO4 minus. Is it amphiprotic? We just have to check that. So it is, right? Because it can gain a proton and it would form H2PO4 minus, and it can also lose a proton. Yeah, because it still has that extra proton, so it can become H plus and PO4 3 minus. So it's both, yeah, amphiprotic and amphoteric. And usually amphiprotic species, they would come from polyprotic acids, that, you know, the acids that have more than one proton, for example H2SO4, H3PO4. So HSO4 minus would also be an example, yeah, of the substance that can both gain and lose a proton. Fine, okay. That's okay. And we have okay, we have 4 more questions, no, 6, I think 6 more questions or something. Well, let's see. So oxidation numbers can be used Okay, like that. Oxidation numbers can be used to balance equations. Chlorine and hot aqueous sodium hydroxide react to produce chloride ions. Okay, whatever. What are the values of the coefficients? Uh, okay, well, what are the values of the coefficients? We need to balance it, but we could balance it with, we have in IB you don't really learn how to balance equations in basic conditions. That's why let's balance it just using oxidation states. Yeah. Again, this is not generally studied. I will teach you now how to balance it fast using oxidation states. If you don't like the method, you can just guess the coefficients. Or you can maybe check like A, do coefficients work, B, do they work, and so on. But remember, when you're balancing equations that have ions, you not only have to balance the atoms, but you also have to balance the charge. Yeah, so the charge on the left must equal to the charge on the right. Okay, how I will balance it. So I know that chlorine changes oxidation state from 0 to -1. Yeah, to -1, which means that it should have gained 1 electron. And also chlorine changes its oxidation state to +5. Yeah, so chlorine changes oxidation state to +5, so it means that it lost 5 electrons. Right, and the number of electrons gained must equal to the number of electrons lost, which means that I would have to put 5 in front of Cl minus, right? Because it has to, like, I have to have 5 things, like 5 electrons gained, so it means that I would form 5 Cl minuses. So if I put a 5 here, then I would have 1 here, right? Because I have 1 in front of Cl plus 5. And then in total I have 6 chlorines, so I would put a 3 here. Well, and the rest, do I need the T? Let's see, maybe that's enough and I don't have to. T is not even there. Yeah, so I don't care about the T. So P is 3, R is 5, yeah, so A then. S is 1. And T, I don't need it. I don't waste time to, I don't have to balance it. 35. The chemistry of group 7 elements often involves redox process. 7 is like 17, yeah, you know, this one. Not that, 17. Involves redox processes. Which of the following statements is correct? Okay, let's see. Bromine can oxidize chloride ions. A lot of things can go wrong with these questions. Bromine, I-N-E, means that it's a diatomic thing, so Br2. Can oxidize chloride. Chloride. Ide tells you that it's a halide. Yes, so it's like a Cl minus, Br minus, F minus, I minus plus Cl minus. Will this work? Remember, the rule is that the more reactive halogen would displace the less reactive from its salt. Yeah, so this is the halogen. This is a salt of a halogen. Yeah, NaCl, NaBr. And bromine would react and it would displace Cl minus if bromine is more reactive. But bromine is not more reactive because it's below chlorine in the periodic table, and reactivity of halogens decreases down the group. So the reaction will not happen because bromine is less reactive than chlorine. Next one. Iodide ions are the weakest reducing agents of the first 4 in group 7. Iodide. Okay, so reducing agent, what does it mean? Reducing agent is being oxidized, so it's losing electrons, right? If you compare the ability to lose electrons of F minus, Cl minus, Br minus, they all can lose electrons, but I minus, it has the largest radius, so the outer electron is attracted the worst. Yeah, so it means that it would lose electrons the easiest. I minus loses electrons the easiest, so it's the strongest reducing agent. But this kind of thing, of course, it's better to just know, yeah, that reducing power of halides, it increases down the group. But if you don't know, you can figure it out from, basic concept of how electron is attracted. In interaction with water, chlorine is oxidized and reduced. Yes, that's a yes. That's a disproportionation reaction, a very famous one. So you have chlorine reacting with water to form HCl and HClO, which is balanced, so C is right. Fluorine is a weaker oxidizing agent than chlorine. That's wrong, yeah, because down the group oxidizing power decreases. So fluorine is the strongest oxidizing agent. Next question. 36. Ethane. reacts with bromine in the presence of UV light to form dibromoethane and hydrogen bromide. Okay, let's see. So ethane reacts with with bromine in the UV light to form dibromoethane. So C2H4Br2, and then it means that it must form 2HBr. That's a what? That's a free radical substitution of alkanes reaction, right? And it can substitute as many of the hydrogens as you want, as there are bromine atoms, yeah, as there are bromine molecules. So the reaction proceeds via free radical substitution involving initiation, propagation, termination. What's the minimum number of free radical mechanism steps to produce dibromoethane? So this dibromoethane, it doesn't form in one step. So first you form like monobromoethane, yes, so one just bromoethane with one Br, and then you form dibromoethane. So what do we need? We need one initiation step to get bromine radicals, and then two propagation steps to form one bromoethane, yeah, and then we need another two propagation steps to form from to form from one bromoethane dibromoethane. Yeah, so one initiation, two propagations, and two propagations to form the second product. So 1, 2, and 2. That's initiation, that's propagation, that's propagation. So it's a 5. We will study it in a bit more detail when we do mechanisms for alkanes. Yeah. Right. Next question. Which of these compounds would act as a nucleophile? Okay, nucleophile is what? By definition, nucleophile. So, I mean, it likes positive charge. Yeah, nucleus, it's positive, so it likes the positive charge, and so nucleophile would be a lone pair, electron pair donor. Donor, so a thing that can donate electrons, well, obviously, OH minus, right? Because oxygen has lone pairs. Aluminium, it's a metal, doesn't donate, usually loses electrons. This is definitely, and no, doesn't even have lone pairs. H plus has no electrons to donate at all. So the only option is C, and it's a very famous nucleophile. You need to know it even for SL. It's the most common nucleophile in, these nucleophilic substitution reactions. 38. Isomers X and Y both react with HBr. A mixture of X and Y's reacted with HBr. Which three structures represent three different possible products of this reaction? Okay, well, let's see. For this one, I think I'd have to redraw it maybe. Let's redraw. Okay, I'll just copy this. So we need to react X and Y with HBr and see what the products are, right? Okay, let's do it. So, and then compare. Right, so X. I'll redraw it so that I see the straight chain better. So X, it's CH3, C double bond C, BR, CH3. I just redrew that, yeah, so CH3, C double bond C, BR, CH3. With HBr, what would the products be? So there are two possible products, right? Because H could go to the first carbon, and then Br would go to the second carbon, or the other way around. Br goes to the first one, H goes to the second one. So the first possible product is CH3, CH3. So I'll maybe color code. So let's say H goes to this one, and then double bond is gone, right? Because it's addition reaction. That's how alkenes react. If you're unsure why this goes like this, why I'm breaking the double bond, you need to revise electrophilic addition reactions of alkenes. So alkenes always react like that. They break the double bond and then you attach like whatever you're adding. So H goes here, Br goes there. So that's the first product. Then again from X you can have another product. CH3 double bond C. Br. So another product would be when we attach, okay, I'll just color code them again. H, so I would attach now H to the first carbon, and then that one to the second. So CH3, CCH3. Then here I would put Br. Again, double bond is gone, and then Br, Br, and H is there. And you see that these are different products, right? Because this is 1,1,1 tribromo and then 2-methyl propane, whatever that is. And this is 1,1,2 tribromo. Yes, so bromine is on the other carbon. So that's two products. And then from the other one, from Y, what do we have? We have CH3, CBr double bond, CBr. CH3, and then again I attach HBr. Here I have one product because it doesn't matter where I put H, here or there. It's in any case I would have like 2, 2, 3 dibromo, right? Because I would just start numbering from the side where I have two bromines. If you're unsure what I'm talking about, you have to draw it and see. Yeah, so try to add H here, Br there, and then swap them around. You'll see that you'll end up with the same molecule. So Br, Br, CH3, double bond is gone, then H, Br. Yep. Br, H. Again, if you swap them around, that would be the same molecule. Well, right, let's check now. So I have, okay, now this is a little bit of a challenge because I have to compare. So I do have this one. Yeah, that's the first one. CH3, CH3, BRB. Yeah, so when I have three bromines on one carbon and then CH3 on the next one. So I have this one, I have this one. I don't have this one. Oh, actually, yeah, maybe that's easier. So you see, I don't have a substance with four bromines, so it's not C. Yeah, that's wrong. Four bromines. And do I have I don't have that one because it only has two bromines. I have to have three bromines everywhere, so it's not A. What else? This is 3, this is 3, that's fine. Here it's 3 bromines, 3 bromines. No, C I already excluded, right? C I excluded, then D. So it's either B or D. Now this is 3 bromines, this is 3 bromines, this is 3 bromines. Okay, so now we have to check. This one, D option, does not have this molecule, which we established that we should have, right? It has bromines on different carbons. 3 bromines are always on different carbons. So it must be B then. Let's double check. So this one we have, what is this one? This is 2Br and then C. It's this one. Yeah, 2 BRs and Br on the other one. And this one is, yeah, from the Y. Yeah, 2 bromines in the second one, 1 bromine in the third one. It's this one. But again, the easiest way to do this question would be to exclude the things that have more than 3 or less than 3 bromines, right? Because we see that all our isomers have 3 bromines. And then you have to just decode the structures. Okay, we're almost there. This is a very long stream. I don't know why it's taking me this long. Maybe I'll stop explaining that many things. I don't know, maybe if I should cut my explanation short, just let me know, because I actually initially planned to get one paper in one stream, but it just doesn't work. It's the second stream already and I just cannot use less than an hour, it feels like. Okay, let's see. So 2 questions left and then you can go. So limonene is an oil formed, okay, whatever. And so that's the structure. Which product is formed when excess of bromine liquid reacts with limonene at room temperature in the dark? For this, you have to know the properties of alkenes, right? Because this is essentially an alkene. So you have 2 double bonds. This reacts as an alkene, this reacts as an alkene. It's not benzene, guys. I hope you see it's not benzene. There is no circle, there are no 3 double bonds. Yeah, no, it's not benzene. It's 1 double bond, cycloalkene. 1 double bond, it would react just like normal alkene would. And I'm adding bromine. Well, I'll just draw it here. So to add bromine, I would just remove a double bond. That's a single bond now. Add Br here, Br there, and do the same here. Remove the double bond, put Br here, and Br there. I just have to find which option works. Definitely not A. A is what? I don't know, A is weird. They didn't remove the double bond, they kind of did free radical substitution with this carbon, so not A. In B, this bond is still double. No. How do I know? Both bonds would react because it's excess, right? Excess, then C. C is wrong. This bond is untouched. Yeah, so not C. Well, must be D then. D is right. Yeah. 2 bromines, double bonds are gone. All good. And the last question, everyone's favorite skeletal formulas. Which compound has an NMR of 84.18 and will react with HBr to give a product with an NMR of 165.09? Well, let's see. So, first of all, if it reacts with HBr, I know that it's not A is cycloalkane. It's just an alkane. It can only undergo free radical substitution, at least from what we know in IB board. It's not C. C is a ketone. You see, it's not a carbon-carbon double bond. It's carbon-oxygen double bond. We haven't studied those, and it would not react with HBr. If you're unsure, well, maybe you can check. But I know that ketones don't react with HBr. And so it would be either B or D. Just as practice, I will redraw these formulas into normal, let's do even displayed formulas, just for practice. Let's do that. So uh, I will now put dots where the carbon atoms are. Okay, so this is a carbon, 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 carbon. So I have 1, 2, 3, 4, 5, 6, 7, 8 carbons. 4, 5, 6, 7. Oh my gosh, this is so many carbons. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 8 carbons. I will even number them. I don't know if that's the correct side, but just for my just to draw it out. Yeah, so you know that you have to number from the side closest to the double bond, but to understand that you need to start somewhere, right? Just let's number from this side. So between the fourth and the fifth carbon, I have a double bond. So this is my number 1, 2, 3, 4, 5. So the double bond is between the fourth and the fifth double bond, and that's it. And the rest would be hydrogens, right? So then you just put the hydrogens 1, 2, 3, 1, 2, so that each carbon has 4 bonds. 1, 2, 1. This needs 1, right? Because it has a double bond already, so it's 1, 2, 3, 4 in total. 1, this needs 2, 2, and this one needs 3 to make it 4. This is definitely more than 84 because it already has 1, 2, 3, 4, 5, 6, 7, 8 carbons. Each carbon is 12, and then plus hydrogen, so that's way more than that, yeah. And so it must be D then. But again, you can double check, yeah. I don't know why they've given so many, like why did they give this? This is completely irrelevant because you just the information that it can react with HBr, it is useful because I excluded A and C, but then I don't need to know the molar mass of the product because B and D, they differ in molar mass, so I can just do it based on that. Okay, that's done. Right, so remember, if you're watching this, as I should have said it in the beginning, though. So I will link the paper that you can download from Save My Exams. Yeah, I'll just link the PDF there, so you can solve it on your own and then watch the stream. But yes, that should have been said in the beginning. And next time probably would have a lesson for A levels. Maybe IB. Just if you can give me some feedback, which would you prefer? So do I have more IB students or more A level students? I'll try to continue with both, but we'll see how it goes. Now it's the summer, so my schedule is much better in terms of lessons, but I am marking A-level exams. I think I start on Monday, so we'll see how much time I have, but I hope I will still try to do at least one stream per week. That's my goal. 2 is better, but I don't promise that. Okay, so thanks for everyone who joined live, and see you next time.